Log on, tune in, find out. Another good idea from Cambridge.
So here's what I will do today. First of all, I will finish a couple of things from yesterday, and then I will talk about the stable hyperplane arrangements with weights. So let me first of all formulate a somewhat different theorem about stable toric varieties, different from what I told you before. And then I will explain why it's the same, why they're equivalent. So here's the setup. Oh, that's not what I wanted. Here's the setup. So I will work over complex numbers so that I can explain better. But everything is over integers or a field of any characteristic, etc. So we will start with a torus. Torus will be just a power of C star, and then we will suppose that it acts on some projective space and also on O of 1. So we have a linearization. And then let's say we have a closed subvariety in Pn. Then in this situation, there is a moment map. So there is a moment map on the projective space. And there is a moment map on this variety. And the image of a moment map is an integral polytope. So lattice polytope in Rn. And so there is a lattice here, Zn. This is the lattice of characters of this torus. So it's a situation similar to what we had last time. So there is some lattice polytope. It's the moment polytope. It's the same polytope that appeared last time for toric varieties. So here's the theorem. That there exists a coarse moduli space, and I will denote it by mt of VQ. This is a moduli space of stable toric varieties X with a finite morphism, T equivariant morphism to V. And so what you should compare it to is the following theorem, that on the other hand there exists a fine moduli space which is called the Toric-Hilbert scheme. Hilb H of VQ. Yeah, so how does Q participate here? So these are stable toric varieties of type Q. So they correspond to this polytope or to some subdivisions of this polytope. And on the other hand, there is a Toric-Hilbert scheme parameterizing T equivariant subschemes, closed subschemes, Z in V, and again of type Q. So what's different in these two theorems? One difference is that for stable toric varieties, for this moduli space, this morphism is finite, and for this toric, for the toric Hilbert scheme, you're really looking at subschemes. So the morphism is an embedding. And on the other hand, the stable toric varieties are reduced by definition. So they have nice singularities. They even have semi-low canonical singularities. And these subschemes, these toric subschemes, they're possibly non-reduced. So that's the difference. So why the difference? So let me explain that part. Let's say you have a toric variety. So this is toric, projective, polarized. So L is an ample line bundle. Then the space of zero sections is so this corresponds to a polytope Q. Some lattice polytope. And the space of sections here splits into eigenspaces. They're one-dimensional, and each of these eigenspaces corresponds to a character, to an integral point here. So it goes over the integral points in this polytope. So that's true for any toric projective polarized variety. And then you have a moment map, as I said, and you also have a map. So this linear system L is free, and it defines a morphism. I'll call it pi, because it's the same pi as that pi. It's a morphism to a projective space. N is the number of these integral points minus 1. And this morphism is finite. And it's usually not an embedding. And so that's exactly the source of differences between the two versions, and why you must make a choice. And so your choice is that either you work with nice varieties, toric variety is a very nice non-singular maybe variety or normal variety, but then your natural morphism is only finite. Or you decide to work with an embedded subscheme, but then that subscheme is forced to have nilpotence. And so it's one or the other. Either a subscheme which has nasty singularities, or a nice variety but with a finite morphism. So that's it. So there are these criteria, there are combinatorial conditions for this PL to be an embedding. Let me mention that it doesn't have to be even. So what is the degree of this morphism, for example? The degree is the index in Z to the n of the subgroup generated by these differences of integral points. So in dimension 2, it's always 1. But in dimension 3, you can easily find an example where this degree is not 1. Okay? So that's the difference. So what is the relation two stable pairs, the answer to that is the following. So if you have X, a stable toric variety, then a divisor D, which does not contain any T orbits, so that was the condition yesterday, so that you have a stable pair, so that was a stable pair. So to have such a divisor is the same as to give a morphism from X, a T equivariant morphism to Pn. The data is the same, so maybe I will let you think about that. So this was a stable pair, and this is a stable map. Stable map is when dualizing sheaf for this log canonical divisor is relatively ample. But for a finite morphism, any line bundle is ample, relatively. And maybe go in one direction. I'll tell you what one direction is. If you have a map like this, then this divisor is the pullback of this equation. So that gives you a divisor which does not contain any T orbits. And then you can go also the other way. So now once you see this, then it's not hard to give a proof of this statement. So for the toric Hilbert scheme, what you're looking at you have this polynomial ring for your projective space, so that's a capital N, and you're looking for all quotients, so for all algebras which are quotients, and this has to be Z ungraded. And moreover, the graded pieces are all have dimension either 0 or 1. So 1 when they're in the cone over Q. And for this version, you're looking at no longer surjections, but algebras, so that this homomorphism is finite. So it's finite over the image. And again, Z ungraded. And fibers, geometric fibers, reduced. And so once you have this version, for example, then it's you can pass to this version quite easily. Or the toric Hilbert scheme can be constructed by hand, so to say. You just a surjection like this, you just need to see what the relations are between images of x0 through xm. And these relations give you moduli. And so same here, with a slight complication that this is a finite morphism. Okay, so nobody is asking any questions today, so it's going very, very quickly. So
what's the relation between two moduli spaces? There is
a map. So there is no map either way, but there is an open subset which is common to both. And that's exactly corresponds to those polytopes or subdivisions, I should say, corresponds to subdivisions where these polytopes are nice. And nice means precisely in this sense. Nice means that for the corresponding toric variety, this is not just a finite morphism, but actually a closed embedding. So that's a combinatorial condition on polytopes, which is always satisfied. For example, it's always satisfied in dimension 2. It's also always satisfied for metroid polytopes. So there are, if you do it in general, then any kind of polytopes may appear here. But if you do it for a specific variety, as I will in a few minutes, when you do it for the variety V, which is the Grassmannian, then the image of the moment map in this case is a Metroid polytope, is what's called the hypersimplex. And all the polytopes that appear in the subdivisions, they are Metroid polytopes. And they are nice in this sense, that they are strongly generating, strongly unimodular. All the toric varieties that appear, they come with an embedding into a projective space. And so in that case, there is no difference. So this toric Hilbert scheme is precisely the same as that. You are well familiar with another class of polytopes, which are super nice, and those that appear in the toric or tropical Torelli map. So those polytopes, I would call them also Metroid polytopes. They come from integral Metroids. So again, they are nice, and there are none of these combinatorial complications. And then there are, if you go more generally, then there are all kinds of counterexamples that you can construct. Now, for C, here's what I will do for degenerations of abelian varieties. Yesterday, I defined the secondary fan, and if you recall, you look at height functions. They form a vector space. You divide that vector space by linear functions. So there is this space where the height functions live. And every height function on the polytope defines some subdivision of Q. And that gives you a fan. So you look at those, you divide your height functions into pieces that correspond to the same subdivision. That was the definition of the secondary fan. So let me give a definition of the second Voronoi fan. And once I've done this, maybe you can appreciate how similar the definition looks. And maybe you can agree with me that it's the same definition. So here's what we will do. We will look at, OK, this was yesterday. And this will be today. No, this will be today. And this was yesterday. And yesterday I defined the secondary fan. And so what I looked at, height functions which were, you look at the integral points in the polytope and are valued, and you associate to this height function. So here's, say, your polytope. Here's the height function, and then you look at the roof. Okay, roof. At the roof. And this roof subdivides your polytope into smaller polytopes. So that gives you a subdivision then into QIs. So that for every function you get this subdivision, and therefore this set of all such height functions is R to the n. I denoted it. Then you divide by linear functions. That's R n minus 1. So you get R to n minus n plus 1. Sorry, R n minus n minus 1. And so on this space, you get a fan on this space. The cones are subsets where you get the same fixed subdivision. So here's what you can do quite similarly. You can look at the height functions which are defined on Zn, on the whole Zn. I will just do it for z. So right now there is an infinite dimension, but we will make a restriction. We will say that H is quadratic, non-homogeneous, such that if you look at the homogeneous part, at the quadratic part, then it's positive definite. Okay, semi-positive definite. So you look at such quadratic forms. Now they what is the dimension of these quadratic forms? For the quadratic part, you have n times n plus 1 squared. And then for the linear, you have n. And then for the constants, you have 1. So let me try. So there is a quadratic function. And so instead of the roof, I could have inverted this and looked at the bottom. So I will look at the bottom. So I will look at the convex hull of all these points, and I will look at the bottom. And so what this does, this gives a subdivision this gives a subdivision of Rn. So some subdivision of Rn into polytopes. Polytopes if this quadratic form is really positive definite. Now, if you add or subtract a linear function again, then this subdivision will not change, right? Just the same as there. So you can divide by linear functions, and that will knock off n plus 1. And so you have a space of this dimension. And you have, well, you subdivided them into somehow, into some subsets. Now, this subdivision is Zn periodic. How do you see that? Well, if you take a quadratic function and you shift it by a vector, then you get the same quadratic function plus a linear function. That's because derivative of a quadratic function is linear because of that. And so therefore, this subdivision is periodic with respect to the same lattice z to the n. So you get these subdivisions. These subdivisions have a name. So these are Delaunay subdivisions. And this fan has a name, so that it's called the second Voronoi fan. So what this construction, as you can see, is precisely the construction for the second Voronoi fan. And now this secondary fan describes degenerations of stable toric varieties. And the claim here is that this fan describes geometric degenerations of abelian varieties. And the reason for that is, I will outline the reason. If you have an abelian variety, then it's a quotient of c to the g, well, I'll do the same n, c to the n modulo z to the 2n. And this you can do in two steps. You can first divide by z to the n and then by the remaining c to the n. And c mod z is the same as c star. And so what this is this is a version sort of a toric variety. There is an action of c star to the n, so it's sort of like a toric variety. Only it's a quotient modulo it should be Zn periodic. And that's exactly near the boundary of a degeneration. The situation is toroidal. Now the divisor that appears here is it's the theta divisor. So it's the zeros of a theta function. And a theta function in this language, if you use the C star to the n action, it can be written as sum of eigenfunctions. And the coefficients Cm are quadratic non-homogeneous in M. And so therefore your height function has to be quadratic non-homogeneous in M. And so that's how it appears. So that's, I hope that this is, for those of you who have never seen this, this is a tantalizing hint for the general theory. So let me, I'll stop for a question. And otherwise, let me move on to weighted stable curves and weighted stable hyperplane arrangements. So let me start with curves, and that case is due to Hassett, the definition and the construction of the moduli space. He did it for any genus G, but I will just do it in genus 0, because first of all, it's easier, and this is the richest case. So you see the most. And also, number 2 will be a direct generalization of number 1. So if you have X, and it's a stable, okay, let's start with a smooth genus G, G curve. Then, okay, X is just a P1, right? And if genus 0, and a nodal curve of genus 0, that means that X is a tree of P1s. So that's our curve. And it looks like this. A tree. Then I will add n points, B1, Bn. These will be points. And then I will add the weights. These are weights. The whole collection I will denote by beta. And each of these weights will be a rational number between 0 and 1. So these are the weights. So in the definition, in the general definition of stable pairs, there were 2 conditions. One was that the condition that the pair XB has SLC singularities. And the other condition was that Kx plus B is ample. So let's see what those conditions mean. So the first condition in this case means that, first of all, these points BI are not the nodes. And if, but they may coincide. So if some of these points coincide, so come together, then the sum of these weights have to be less or equal than 1. So that's the condition. This is the log canonical condition at this point, that you have no more than 1. And the second condition, Kx plus B ample, that means that if we compute the degree of Kx plus B on one component E, so this will be E, then this number should be positive. It's for every E in X. So this number is easy to compute. It's twice the arithmetic genus of the curve. but it's a tree of p1s, so twice the arithmetic genus minus 2 for p1 is minus 2, and then it's plus this sum of plus e times x minus e, this number, and then sum of the weights where the points are in E. So that's the condition. So on every component, this sum has to be greater than 2. This counts the points of intersection, and then this counts all the weights on this curve. That should be a positive number. So that's the stability condition. If all the weights are 1, then this is the usual condition that this number should be at least 3, greater than 2, at least 3. So you recover the usual definition. So here's the theorem of Hassett. I'll formulate it all as one big theorem, so let's do some preparations. First of all, there is a weight domain, D. So this will be the possibilities for the weights. This is where betas will live. So what are the conditions? So you have B1 through Bn, such that each bi is between 0 and 1, and sum of bi's should be bigger than 2. So it already, that's just saying that the total degree is positive. So these are the possibilities for betas. And then we will have a chamber decomposition. So we will divide this into chambers. And the chambers are as follows. So for every subset in 1 through n, for every finite subset here, the sum of bi's in this set equals 1. So these are some hyperplanes in this space, and that divides the chamber into finitely, the whole domain into finitely many chambers. And then the theorem of Hassett is as follows. So for every beta in this domain D, there exists the moduli space M0 beta bar. This is a fine moduli space of beta stable weighted curves of genus 0. It is smooth and projective. If beta and beta prime are in the same chamber, then the moduli spaces are the same. So if you stay in the same chamber, then you get the same moduli. If you go any lower, so for any beta bigger than beta prime, there's a diagram like this. So m beta maps to m beta prime. And the universal family maps to a universal family. So everything commutes like that. And maybe the last part of this theorem tells you, of his theory, tells you what happens on the bottom. So what happens if the weight is very small? So if beta is alpha plus epsilon, so this will be alpha, and this will be beta, nearby, and beta is generic, or alpha is generic. So generic means it's not on one of these hyperplanes. That's generic. Then this space is a GIT quotient. And you can write this as a GIT quotient of product of P1s or GIT quotient of a Grassmannian, G2n, by the torus. The torus here is C star to the n modulo diagonal C star. Now, when you write these GIT quotients, you have to make a choice of either an ample line bundle or linearization. And these such choices are encoded precisely by a number by an element here, by some point on this face. And so that's the one that appears. Okay, so a very nice complete picture. I should give one example just for people who haven't seen this stuff before. So let's start let's say you start with a picture like this, and there are some weights 1, 1, 1, and then maybe also 1, 1, 1, so you have a stable curve. And then you go ahead and decrease these weights. And then on this curve E, the stability condition was, remember, B1 plus B2 plus B3 plus 1 coming from here should be bigger than 2. So the weights have to add up to at least 1. That's the stability condition. And so if you decrease them enough so that you have less or equal than 1, then something has to happen. And what happens is this component collapses, and the 3 points now coincide. And at this point, remember, the singularity condition was precisely that the sum of the weights should be at most 1, less or equal than 1. And so this is how it all fits. So you trade this picture for this picture, and in the definition, this numerical condition becomes the singularity condition on the curve. So that's all that happens. Yep.
Near this alpha is this GIT quotient. Then that has associated to it wall crossing and chambers and so on, but that's not the same as, you're not saying they're all.
Right. So every time you see a chamber decomposition, right, you think GIT, right? Or most people. I know, by you, I mean me. So. Okay, every time I see a chamber decomposition, I think GIT, or maybe VGIT. And V stands for variation, right? Variation of GIT. So in GIT, there are some choices: an ample line bundle and linearization. And so you vary, and you have this wall crossing. Well, what kinds of crossing? So if you do that for the Grassmannian, then the choices are described not by this chamber, but only by this face. And so therefore, this variation of GIT is precisely, you see this chamber decomposition. But you don't see this domain does not appear. And so the natural question is, what about this domain? Is there a GIT problem that precisely describes that? And the answer is yes. And what?
But it's not this SL2.
It's for the torus. And so what you should be looking at, maybe it can, I think it can be done with SL2 as well. But it's the GIT for the universal family over the Grassmannian. So over the Grassmannian, you have a family of linear spaces. So if you do the GIT for that space, then that's exactly what you will see. And that's the answer. So somehow that turns out to be the heart of the matter. So all of this is the aim of number 4, or number 2, is to generalize all of this to higher dimensions. And so every single piece here, including this GIT and this variation and this chamber decomposition, will be generalized. Mm-hmm.
As you move beta, right?
So you see, when things collapse, it's still a tree of P1s, right?
When
So-
all the weights are 1.
When all the weights are 1, then this is the Dilling, Mumford, Knudsen, the usual space.
You must have a certain map for other chamber models.
Exactly. So that's the statement here, and this is how it works. You start maybe with all the weights 1, and then decrease the weights. So this is what happens to the curves. Now let's see what happens to the moduli. Okay. Let's say you started with all the weights 1, and you decrease the weights a little bit. Now what is the map on the moduli? Now, just compare these two pictures. And the statement is that in this picture, there are more moduli than here. Because in this picture, on this P1, there are 4 points. And 4 points have a one-dimensional moduli. And here, that moduli disappeared. So therefore, there is a surjective map, which is not an isomorphism. It turns out that every time you cross a wall generically, then it's just a smooth blow-up that happens. So going backwards, it's just a simple, smooth blow-up. So all of these spaces are non-singular all the way through. And there are connections between them. It's the blow-up. You look here at the locus of such configurations where these 3 points coincide. It's a closed subset in the moduli. That's what you blow up to get that.
So they are all birational to each other?
Absolutely. They're all birational. And for some specific weights, you just get the projective space. And so one of these, for some low B, you just get a projective space. And here's your description of M0 and bar as a successive blow-up of a projective space. And Kapranov gave such a description a long time ago, but this is how it can be explained with the weights very, very easily, very nicely.
So you mean when you construct a P1, you can see it as a blow-up in your mapping?
So let's call this beta and this beta prime. Then the point is that the statement is that this is the blow-up of beta prime along some z. Z is the subset in here. It's precisely the subset where these 3 points coincide. It's a proper closed subset. That's what you need to blow up. It has codimension, number of these points minus 1. So here it has codimension 2. When you blow up, you have a P1 fibration, your exceptional divisor. So that's so for curves, as frequently happens, the picture for curves is easy and beautiful, and simple to prove, and really joy to work with. And then when you do these things for higher dimensions, then your your moduli become arbitrarily singular, and the combinatorial difficulties explode. So the moduli in higher dimensions will be very singular in general and will not be reducible, etc. Okay, so what's the generalization? So how what do you generalize? So you start at P1 and endpoints. So what is the higher dimensional analog of that? And it will be PR minus 1 and n hyperplanes, B1 through Bn. So that's the generalization that I will consider, and for, well, anyhow, for which I can prove a theorem. And the reason I can prove this theorem is because there is this interpretation in terms of the Grassmannian and in terms of the universal family over the Grassmannian. So you have n hyperplanes, they may coincide, they can intersect very, very badly. The first condition is to understand when is it stable? What is that equivalent to? There were two conditions. The first condition was that this pair with the weights is log canonical. And the second condition was that the canonical class of projective space plus some of these, that has to be ample. And the second condition is very easy, right? It just says that sum of BIs have to be bigger than R, because that's the canonical class of the projective space. And remember, in the previous case, it was bigger than 2. And the second condition is as follows. So for every subset in 1 through n, the sum of BIs in this set has to be less or equal than the codimension of the intersections of these hyperplanes. So here's what it means. If some lines coincide, then the codimension is 1. And so the sum of BIs here has to be less or equal than 1. This is as before. And here the intersection has codimension 2. So for this to be log canonical, the sum should be less or equal than 2. So that's the condition. And you continue. So these are the log. That's when a projective space with hyperplanes is stable. It's quite easy, but well, that's what it is. So we will define a similar domain, and I will just copy Bn. So each BI is between 0 and 1, and sum of BIs is bigger than R. And we will have a chamber decomposition. So for every I look at the hyperplanes where they adapt to K, and now there will be more possibilities for K. So if I work with planes, then what the condition when something adds up to 1 and when something adds up to 2 are critical values. So that's the chamber decomposition. And just as before, the explanation for this chamber decomposition is that this describes the VGIT for the universal family over the Grassmannian GRN. That's where it comes from. And then the statement is that for every beta in D, there exists a moduli space, this m beta Rn. That's my notation of stable weighted hyperplane arrangements. Beta stable. Okay, what else? Nothing to write there. They are not smooth. They are projective. Okay, so they are projective, but quite singular, unless the weight is small. Now, if beta and beta prime are in the same chamber, then you have the same moduli space. And so the next statement is not true either. So instead, what is true is that if beta prime is in the closure of the chamber for beta, then you have this diagram. So you have, okay, I'll just split it into two statements. You have a map on the moduli spaces and the map on the universal families. And if beta prime is bigger than beta, then this map, let's call it phi is birational. Now, if beta is bigger than m prime, then you still have a map on the moduli spaces. And on the universal families, this is no longer regular, but this is a sequence of contractions and flips. So in the one-dimensional case, when you cross in this direction, from that chamber to that chamber, it's just a contraction, both for moduli and for the universal family. And in the higher dimensional situation, this is, instead of one step, this is two steps. And so this map is a contraction, and then this map is a contraction. And so that opposite map is a small extraction. So it's like a flip that happens here. And then for the small weights, if beta is alpha plus epsilon, and alpha is of length r, so is on the bottom, and generic, then this moduli space is the GIT quotient of PR minus 1 n copies by SLR for alpha, and also the Grassmannian GRN modulo torus by alpha. So that part is exactly the same. So that's the statement. Now, there are these weighted hyperplane arrangements, and I haven't defined them, but the main property about them that they are SLC and K plus B is ample. So they are as expected, as predicted by the minimal model program. That's exactly what they are. But otherwise, so I don't give any intrinsic definition for them. It's just what happens here is that coming from Grassmannians and from GIT, there is an explicit family that comes from projective geometry, and you just observe that every fiber in this family is a stable pair. But but isn't that what I explained last time and also on Monday? That this construction with the MMP for the one-parameter degenerating family, it gives you a unique limit for every one-parameter degeneration. And this limit is like that. It has SLC singularities and K plus B is M. So then, that was the prediction of MMP, that if you look at the functor of stable pairs in this sense, then it should be a nice projective, nice proper moduli space. And so this is another example, and it's constructed without using any MMP. So many features are just what you expect. Also these things, about contractions and flips, but no MMP is involved in the proof. So what I will do right now, I will show you a few examples. So I'll just show you. So there is sort of a new world. So there are lots of things to play with here. Now, as far as the proof, I'll give you an idea of the proof tomorrow, and then tomorrow I will show you applications of this. Applications are to classical questions or to moduli of surfaces of general type, and they are quite pleasant applications. And then by the end of tomorrow, I will catch up to my schedule, to my, that I imposed on myself. And on Friday, we will do, instead of nice examples, we will do honest work. And so I'll try to explain how this construction of such moduli of stable pairs can be done for surfaces and in general, where we're not so fortunate, where we don't have a torus action or we don't have Grassmannians to help us. So I know next to nothing about the effective cones, ample cones, etc. of these moduli spaces. I know pretty much nothing. So for genus 0, there is a lot of study. As you know, for M0 and bar, that's the F conjecture, which is still open. And then, but you can ask the same question for all of these weighted spaces, and for some of them it can be answered. There is a lot of lots you can compute and lots of papers. Now, these higher dimensional things, I skipped the part about smooth because it's not true. So these spaces typically have many irreducible components. And they are part of this pathology. Any singularity that you can write down, it appears on these moduli spaces. So any singularity of finite type over Z, any polynomial equations with integral coefficients, there is, that singularity appears. And so they are not equidimensional, et cetera, et cetera. Now, for small betas, they are nice, right? They are just GIT quotients. Okay, so GIT quotients, at least they are normal, and you can say a lot about singularities. So the closer to the bottom, the nicer they are. And maybe for those, you can answer lots of geometric questions. How to deal with the higher ones, it's hard questions. Requires an approach. So let me show you just in a few minutes, let me show you some examples which look almost trivial, but maybe you will appreciate how nice they look. So let's just start with M04, and let me say the most trivial thing there is. And let's say you have 4 points, and then you degenerate this picture, and 2 of those points come together. Okay, and so if the weights are, for this to be stable, the weights have to be less than 1, less or equal than 1. And if this is not satisfied, for example, the weights are 1, 1, then something happens, right? And what happens is you insert, and these 2 points jump on the other curve. And this picture is dual to a picture where the points 3 and 4 come together. And the condition here is that B3 plus B4 should be less or equal than 1. And if you think of it, that's precisely the opposite of this condition. So if you say that sum of BI's is 4, then the negative of this condition is that condition. So they are complementary. And what happens here is points, there is a blow up, and the points 3 and 4 jump on the other curve. And it's the same exact curve. So this is how you get this stable curve, either from here or from there, isomorphically. So let's just do the same in dimension 2 for surfaces, and see what happens. So I will start with 5 lines in P2, and some weights, and let's say 2 of these curves, 1 and 2, now come together, and the curves 3, 4, and 5 somewhere else. So if the condition for being log canonical here is that B1 plus B2, the sum should be less or equal than 1. And if the weights are bigger, then this is not log canonical. Something has to happen. And something like this. And so what happens is, for this line, instead of these lines, a P1 fibration is inserted. This P1 fibration is F1. This is the blow up of P2 at one point. And you still have this P2. And the lines, those 2 lines, they jump on that F1. And these 3 original lines, 3, 4, and 5, what happens to them, they now become reducible. So instead of irreducible, that's the line. These are the lines 3, 4, and 5. And these are the lines 1 and 2. Now, the opposite degeneration to this, the dual degeneration, is when the points 3, 4, and 5 come together. And the condition for log canonical here is that B3 plus B4 plus B5 have to be less or equal than 2. And if instead of, oh, I'm sorry, how come 4? So that was 2 here. So because we're looking in PR minus 1, which is P2, R is 3. So the base case is when they add up to 3, and therefore this is precisely the complementary case to that. And so what happens? Something has to happen. There is this, and then there are some curves 1 and 2 somewhere else. So what happens is that instead of this P2, you replace it by a blow up of P2 at the point P. That's the point P. And therefore, this P2 becomes an F1. And at this point, an extra P2 is inserted. And these lines 3, 4, and 5, now no longer intersect at this point. So therefore, this condition is fixed by this blow up. And then they continue on the other P2. And those lines 1 and 2, well, they stay where they were. And so you get precisely the same picture as that. And so this is a stable hyperplane arrangement. That's an example of how degenerations work. So when you degenerate, there are some conditions that fail in your degeneration. And so for each of these conditions, an irreducible component is inserted. And so so I can draw, pictures like this progressively more and more beautiful, forever. But time is limited. So what I will do next time, first of all, I'll give you an idea of the proof, and I think I'm partial. I think it's a very cool idea, and the key is exactly this universal family, study of the universal family, and GIT for that. And then another coincidence happens, which is not a coincidence, but a deep connection. And it's a connection between GIT and these log canonical singularities between minimum model program. And then I will show you applications of this. And to do these applications, I have to compute lots of such pictures. And fortunately, I have these pictures on my computer, so I can just show you slides, and they're all. There will be lots of pictures tomorrow. Is it possible to get a computer? Okay. All right. And so, but for today, we'll finish.